Physics Practical. In today's video, we are going to be discussing the 2022 National Examination Council Physics Practical. This series will be in two parts. A galvanometer, a value of this resistor will be made with unknown or concealed standard resistor. You have the known standard resistor as R1, then you have the G as your galvanometer. This is how you wire things up. Here's how it goes. The reading 2 and 3. So if the galvanometer indicator is exactly on 0, what that indicates is there is no current flowing through the galvanometer. Then if it is on the left or on the right side, it shows that there's current flowing, but the direction might be different. What that means is if it's on the negative side, the current might be flowing from the top of it might be flowing top down. Then if it is on the positive, if it's on the positive end, it might flow the other direction. But then you're expected to adjust the jaw key until the indicator is exactly on 0, which means the potential difference or there is no flow of current through the galvanometer. So that is the experimental setup. So you set the value on the resistance box, then you adjust the jaw key, and eventually you stop once the indicator is at 0. Once you have the indicator at 0, you measure the value of x. X is the distance between P and J. Putting those values, x and y. The next is the jaw key along the Wheatstone bridge. Then 0. If the potential difference is 0, in other words, if there is no difference in the voltage between these two, if they are the same, there won't be any flow of current. And there's no flow of current along this path. The reading here will be 0. If this is the case, the Wheatstone bridge principle states that if you have the setup, R1 over R2 will be equal to R3 over R4. So let's apply this idea to this experiment. We know that R1 is the 1 ohm standard resistor. But what about R2? What's R2? R2 is the equivalent resistance of these two resistors in parallel. So what that means is R2 is equal to 1 over R, since they are connected in parallel, plus 1 over R naught. So that is R2. Now what about R3? R3 is the resistance due to this resistance wire. In other words, is the resistance Q, that wire, times X divided by cross-sectional area. Then for R4, it is resistivity times Y divided by cross-sectional area. If you simplify, the resistivity and the cross-sectional area will cancel out. So you'll be left with R3 over R4 will be equal to X over Y, given point in time. So which means we can represent X in terms of Y as L minus Y. So this implies that R3 over R4 is equal to L minus Y divided by Y, which means we can take that as L over Y minus is equal to 1 R. If you make R the subject, or let's take this other one to this side. So we're going to get R1 over R minus 1, and minus 1 minus R naught. So this is the to L over R1. By making here's how the graph is going to look like. So the graph is going to look like this. So if this on the y-axis, we're going to have r raised to the power of minus 1 comes the slope s. So given that you know c, so you may be asked to calculate something like this, and that scrape the. And the other thing you want to do is to avoid error reading. You will reduce battery drainage over time. So these are some of the things you should take note of. In the next video, we are going to simulate this. Welcome to the second part of our discussion on the 2022 physics practical. If you haven't watched the first part, I highly recommend you do so right away. In the first part, we talked about the experimental setup, we analyzed the physics lab, electricity meter bridge. So here you have the experimental diagram, and here is the way. Here's where you should connect it. Although it may not be exactly like this, but you should have your standard resistor here. You should have another standard resistor here. Then your resistance box should be here. Then you have your key, your battery, and here you have the potentiometer and the likes. The apparatus should be given as follows. Then here you have the procedure of this experiment. The procedure is quite straightforward. You change the reading on the resistance box. Once you change that reading, you adjust the jockey on this on this potentiometer wire. You adjust it until the reading on the galvanometer is zero. Once you get the reading of zero on the galvanometer, you measure the value of X and also the value of Y. You record all of that. You record X, you record Y, then you record the value of R. Then you change the value of R and repeat the entire process again. So that's basically what the experimental procedure is all about. Then once you are done, you take the reciprocal of R, you take the reciprocal of Y, then you plot the reciprocal of Y against the reciprocal of R against the reciprocal of Y, and that makes up your graph. So we're going to go through all of this using this experiment. So the first thing I want to show you is the setting. You can change the setting and see how the results will change. But for this particular demo, a slider on the left, if you take this up, you increase the resistance on the resistance box. Then if you want to move the galvanometer, the jockey, you switch to X here. Then you move the slider. Once you move the slider, then the jockey moves to whatever point you want it to move. Then you need to don't forget to insert the key by switching it on or off. If it's off, it means the key is not inserted. If it is on, it means the key is inserted. Okay, so what we want to do now is to follow this reading. The first reading is when R is equal to 1. So when R is equal to 1, what do? We just move this slider to 1 here. So the resistance on the resistance box is 1. So what do you do next? What you do is you take you then let's turn on the switch, that is insert the plug. Then we move the jockey along the potentiometer wire until the galvanometer reading is 0. So you move it until you see that the galvanometer is moving towards 0. You can see that the galvanometer is moving towards 0. Then we now have something very close. So is to switch from, so that's at 5 6 roughly this. So the and we do the same, we take the difference 100 minus 35.4, that's 64,176, or we can just say 7 7 0 point, let's say 8 if you approximate to 3 decimal places. So this is what we have as our reading. So we are done with the reading section. So the next section is the graph. To plot the graph, what we want to do is we explain in detail with resistance. The unit is centimeter. Watch our video on how to type 0.005. It is where one of our is. So the next thing you want to do is to determine the slope. To get the slope on any line using this application, you click x-axis is 0.01. point is 0.0. So let's take a look at this K. K is what we got earlier. K is what we got here earlier. So if K happens to be voltage when the circuit is open, once you close the circuit, once current begins to flow, whatever you're getting from your battery is now the terminal potential difference. And that terminal potential difference is going to be less than the EMF due to the internal resistance of the cell. The next question, the last question is all about this. So I'm not going to, let's look at the third question. The third question is just a question about EMF. So if the EMF of a cell is greater than the terminal potential difference, the question is, as long as the internal resistance of that cell is zero, can we say that statement is true? Can we say the EMF is always greater than the terminal potential difference? Well, in this case, the answer is yes, because EMF is the voltage when the circuit is open. Once you close the circuit, once current begins to flow, whatever you're getting from your battery is now the terminal potential difference. And that terminal potential difference is going to be less than the EMF due to the internal resistance of the cell. The next question, the last question is all about this. So I'm not going to get this solved. If you want to get the answer to this and get detailed explanation to this question, get the application, download the application and perform this experiment. So I'm going to submit to see my performance. Okay, so here we have the report. This application provides detailed analysis on how you perform on every aspect of the graph. So in this particular case, I performed well on the reading, I performed well on the graph section, but it appears my intercept is a little bit off. Let's take a look at the y-intercept. Okay, we got a very close result. Then the x-intercept, we got a very good result.